Okay, welcome everybody. This is the video podcast for the respiratory system lab test review. Keep in mind that you do not want to use these materials as a substitute for actually studying the material in the lab manual or for taking advantage of the models available during lab or in biosis. Please take advantage of these resources as they will improve your performance on the lab practical. Okay, we start out with identifying the following respiratory system structures. So if we look at arrow A, we're pointing to the superior, to the middle and inferior nasal conchae. This is the superior nasal concha, the middle and the inferior. So superior, middle, inferior. B is pointing to the external nares. This is the opening into the nasal cavity. There's also a set of internal nares, which is at the back of the nasal cavity and enters into the nasopharynx. C is pointing to the epiglottis. D to the thyroid cartilage here. And E to the chrysoid cartilage here and also down here. Sagittal view of the head. Okay, now we have a look at some more landmarks on the sagittal head model. D again is pointing to the nasal cavity. B is pointing to the true vocal folds or your vocal cords indicated here. C is pointing to the pharynx. Now the pharynx has three regions. The nasopharynx, which is behind the nose, the oropharynx behind the mouth, and the laryngopharynx behind the larynx. If we look at C, what we see are a cavity that also has a connection point to the middle ear. If you look at the top of this particular dotted line, this opening here is actually the opening for the eustachian tube, which connects the throat to the middle ear. Okay, a few more labeled areas for the sagittal head. A is pointing to the frontal sinus. This is a hollow space inside the frontal bone. B, the sphenoidal sinus, which is a hollow space inside the sphenoid bone. Remember that the sphenoid bone is also nicknamed the keystone of the cranium, and as a result, all other bones in the skull articulate with it. C is pointing to the nasopharynx. D is pointing to the oropharynx, and E is pointing to the laryngopharynx. This is an anterior model of the larynx and the trachea below it. This unlabeled arrow here is actually pointing to the epiglottis. A is pointing to the hyoid bone, B to the thyroid cartilage, C to the chrysoid, and D down here to the trachea. This is the thyroid gland. This piece of connective tissue here, this is the thyrohyoid ligament. This is a sagittal view of the same model. A is pointing to the thyroid cartilage. Again, this is a posterior view here, so you can see it. B is pointing to the chrysoid cartilage. Notice that the chrysoid cartilage is rather tall in the posterior aspect and rather narrow in the front. C is pointing to the true vocal folds. D to the hyoid bone. Up here you can tell because you can see a little bit of red bone marrow in the center of the hyoid bone. E is pointing to the epiglottis, and F is pointing to the vestibular folds, the false vocal cords. G is pointing to the arytenoid cartilages, and on top of the arytenoid cartilages, this little tiny cartilage right here, that is called the corniculate cartilage. Looks like a pair of little horns on top of each arytenoid cartilage. The significance of the arytenoid cartilage is that it attaches to the vocal cords, and as those cartilages pivot, they change the tension in the cord, and as a result, the pitch of the voice. Okay, This is a model of the larynx. The soft tissue, or the large part, has been removed. The superficial aspect is on the right in this panel and on the left in this panel. A is pointing to the hyoid bone, B to the thyroid cartilage, C to the chrysoid cartilage, D to the tracheal cartilage, E to the epiglottis, over here, and you can also see it over there, and F to the arytenoid cartilage, again, which is connected to the vocal cords. And there you can see also at the top the corniculate cartilages. Okay, in this panel, A is pointing to the epiglottis, and the name for the opening between these represent here the vocal cords is the glottis. So the epiglottis lies on top of the glottis. This is posterior aspect of the larynx model, the one that lacks the soft tissue. Okay, a couple of more models to take a peek at. This is a model that shows you both the trachea, the larynx, and the primary bronchi. Let's start at the top and work our way down. A is indicating the larynx. B is indicating the trachea. This arrow here is indicating the left primary bronchus. This would be the right primary bronchus. This is a secondary bronchus. It branches off the primary. And then down here, you can see a tertiary bronchus. These colored bifurcations are all tertiary bronchi. So it goes primary, secondary, tertiary, and then they continue to branch quite extensively, quaternary, and so on and so forth, until we get all the way down to the terminal bronchiole, and that ends the conducting division of the respiratory system and provides the gateway now for the respiratory division of the respiratory system, and that's where the gas exchange actually takes place. And that division of the respiratory system begins with the respiratory bronchioles and ends at the alveoli. Okay, this is the back of a lung from the brown torso. A is pointing to a primary bronchus. B is pointing to a pulmonary vein. Note that the pulmonary veins are blue, whereas C pointing to the pulmonary, B is pointing to a pulmonary artery. Note that the pulmonary arteries are blue. C is pointing to a pulmonary vein. Note that the veins in the pulmonary circulation have deoxygenated blood, while the arteries, the arteries carry deoxygenated blood, while the veins carry oxygenated blood. So this is the reverse of the systemic circulation. The same is true if we were to look at the circulation coming from the placenta to the developing embryo and fetus. Okay, so to review: primary bronchus, pulmonary artery, pulmonary vein, diaphragm. This is the back of the lung, the back of the lung. Okay, next question: is this a right or a left lung, and how do you know? Well, this is a left lung for a couple of reasons. Number one, it has two lobes. There's the inferior and there's the superior lobe. This is the oblique fissure, separates the two lobes. And this little indentation here is called the cardiac notch, and it makes room for the heart. So a left lung, a left lung. Okay, this is a sagittal section through the upper respiratory, and what you're looking at here are several different tissue types. Okay, so let's walk through what each of these are indicating. A is pointing to the tracheal lumen. This is where the air goes. Okay. B is pointing to the layer of pseudostratified ciliated columnar epithelium which line the upper respiratory. The significance of the cilia is that they beat the mucus, which traps the particulates in the air that you breathe, moving them up towards the oral cavity, where they can either be expectorated or swallowed. If you look in this panel here, you can see occasional light staining cells. These are the mucus cells, and these are what produce the mucus that the cilia move through the upper respiratory system. This area beneath the pseudostratified ciliated columnar epithelium is the lamina propria. It is a type of connective tissue. And then Superficial to all of those are the cartilage. D is indicating the cartilage. This is hyaline cartilage. These are the tracheal cartilage. This is what holds the upper respiratory system open when you inhale and exhale. Otherwise, it would collapse every time you try to breathe out. Okay, this is a little quick video on lung histology.
This is a lung. A lung is defined as the lower respiratory tract. Where the air passes before it gets into the lung, from the nose to the lung, is defined as the upper respiratory tract. The lung is basically nothing more but air spaces and vascular spaces. The spaces that you see here that are filled with blood, like here, 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 are the vascular spaces, going from a pretty good thick sized pulmonary artery down to smaller arterial branches, and of course veins, which would have even a thinner wall than the artery. But remember, the pulmonary artery system has a low arterial pressure, so the arteries here aren't quite as thick as you'd expect them to be. When we look at the alveoli, you'll see the smallest level of vascular spaces. You'll see capillaries. The air spaces consist of bronchi, bronchioles, respiratory bronchioles, alveolar ducts, and alveoli, going from the larger to the smaller structures respectively. If you see a airflow structure that has cartilage as part of its wall, like we see here, you can call that a bronchus. If you see an airflow structure that does not have cartilage in its wall, and I bet you will find one pretty soon. Here's a little cartilage, so you have to call that a bronchus. Here you see an airflow structure where there's no cartilage, so you can call that a bronchiole. The difference between a bronchus and a bronchiole is whether there is cartilage in the wall or not. When you get to the very, very, very lowest level of air spaces, such as here, 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 these are alveoli. The majority of the cut section of the lung is nothing but alveoli. If you see an area where there is a common vestibule for groups of alveoli, you can call that an alveolar duct. Mid-portion between an alveolar duct and a bronchiole is a respiratory bronchiole, which are sometimes hard to find, and I don't think I want to waste my time trying to do it. But remember, it is the respiratory bronchiole in which the normally ciliated columnar epithelium then becomes cuboidal before it actually becomes squamous to involve the alveoli and alveolar ducts. So let's review it. Here is a bronchus because it has cartilage. Here is its normal columnar ciliated epithelium. Here is the lamina propria. This fat can be regarded as submucosa. I believe you can call the cartilage as actually being in the adventitia. I don't think you could think of the trachea or bronchi as having an actual media. Here is a bronchiole in which, because you do not see cartilage, and it is also filled or lined by an epithelium which is, like in the bronchus, columnar, pseudostratified, and ciliated. Here are actual alveoli, and here is the wall of an alveolus, and you can see all of these little red things stippled in the alveolar wall are actually capillaries. Otherwise, the wall of the alveolus consists of pneumocytes, both type 1 and type 2, as well as an occasional macrophage. Let's see if we could find some of these pneumocytes. A type 1 pneumocyte is actually a sort of small spindly cell that comprises the wall of the capillary. If you see a pneumocyte that looks a little bit foamy, like perhaps here, perhaps here, perhaps here, almost looking like a mesothelial cell or a histiocyte, you call those type 2 because those are the ones that have surfactant. In addition, you can see cells like here, which are called Clara cells, which also have surfactant in the bronchioles as well. I really don't think there's anything here that we have ignored. Perhaps we could take another quick look at the shotgun and see, is there anything on here that we haven't identified? Well, I guess if you want to look at the very edge of the lung, you would have to remember that this is the the visceral pleura, and ultimately, like all pleural, peritoneal, or pericardial surfaces, they would involve having a single layer of mesothelium. I believe you could probably call that a surface mesothelial cell nucleus, and probably there as well, and probably there as well. So we have a visceral epithelial cell as part of the pleura. We can see alveoli. We can see alveolar ducts into which multiple alveoli empty. If we saw ducts containing clearly cuboidal cells, we call those respiratory bronchioles. I don't think we really found any too easily on this slice here. This could possibly be one because these cells look very, very cuboidal. Otherwise, columnar cells are in the bronchi, in the bronchioles, and the rest of these structures are veins, arteries, and capillaries. And I would probably call this a vein because it has a very thin wall. But remember, the pulmonary arteries also have relatively thin walls because it's a low pressure system. I feel very, very comfortable at saying right now, thank you very much.
Okay, this is a peek at a blow-up of a cross-section through lung tissue. And you can see several different structures here. This is low magnification. This is high magnification. So let's start with what A is pointing to. A is pointing to the squamous epithelia, the simple squamous epithelia that line the alveoli. The alveoli are these air sacs. This is where the gas exchange actually takes place. You can see another example of an alveolus up here. Those are the smallest air-filled chambers in these sections. There's one, there's one, there's one, there's one. B is pointing to a respiratory bronchiole. Now, how can you tell that it's a respiratory bronchiole? Well, the chamber is larger, and it's also lined with a cuboidal epithelium, and it also has just the tiniest bit of smooth muscle in it. C is pointing to a blood vessel. This is smooth muscle tissue, and this in here is blood. This is actually a terminal bronchiole, and the reason you can tell is because there's a little bit of cartilage surrounding this particular tube. In addition, if you look very closely, you can see that this is pseudostratified ciliated columnar epithelium, which is characteristic of the tissue that lines this particular structure. Okay, moving in, we're going to do a little matching here. Arrow 1 is pointing to a blood vessel here. Arrow 2 is pointing to an alveolar sac. That's basically a cluster of alveoli. Arrow 3 is pointing to individual alveoli, the smallest air-filled chambers. Arrow 4 is pointing to, again, a respiratory bronchiole, And arrow 5 is actually pointing to the alveolar epithelium, which again is simple squamous, one layer of flattened cells with tight junctions between them. Okay, this is an idealized spirograph, and what this measures is the ability of the respiratory system to move in and out a certain volume of air when you inhale and exhale. So what we need to do is when we look at this chart, we need to understand that this area here, these small peaks and valleys, this represents the amount of air that you can move in and out of the lungs with normal breathing. This is called your tidal volume. The amount of air that you can exhale after you've performed a normal exhalation is called your expiratory reserve, and that's indicated by the area from here to here. The amount of air that you can inhale after a normal inhalation is called your inspiratory reserve volume, and that's indicated by the peak going from here to here. We can also make some composite measurements. Your vital capacity is equal to your tidal volume plus your inspiratory reserve plus your expiratory reserve, and so it represents the peak from here all the way down to here. Your total lung capacity includes your vital capacity plus your residual volume. Your residual volume is the amount of air that you cannot blow out of your lungs even with maximal effort, and it serves to give the respiratory system form and structure, and it's this area below where the expiratory reserve ends. So your total lung capacity would be the complete volume going from the bottom of this spirograph all the way to the top, so from here to here. Okay, so if we fill in these values, we get the following. Okay, now the next thing we want to do is take a peek at a typical spirograph recording, and what you're looking at here is, in the old days, the way that these instruments operated was to have a piece of recording paper that was on a rotating drum upon which a pen would draw. And what you do is you would blow into a drum that was attached to this pen, and as you blew into it, what you would do is you would float this drum over a body of liquid. So think of a drum inside the sleeve of another drum, and as you do that, what would happen is that the pen would rise and fall as you inhaled and exhaled. It would draw on the rotating paper, and the paper would spin at a particular speed. Okay, and then what you do is you would plot the volume that you were able to move in and out of the lungs versus the time that it took for you to do that. Okay, so this is time down here in seconds, and this is volume in liters. So if we were to measure the tidal volume on this particular recording, what we'd have to do is look at the way that the vertical axis is partitioned, and you'll notice that for each liter of volume, you have 4 squares. Okay, so each tiny square represents a quarter of a liter, or 250 milliliters. So if we were to measure this person's tidal volume, we would measure 2 squares. Well, 2 squares would represent 500 milliliters. So that's this individual's tidal volume. Okay, 500 milliliters. If we were to measure the expiratory reserve, what would happen is we would measure now the distance from the bottom of the tidal volume to this lower peak. So count the number of squares. 1, 2, 3, 4, 5. Okay, that's 1.25 liters, or 1,250 milliliters. That's the expiratory reserve. The inspiratory reserve would be calculated by measuring the height of this peak. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay, 12 squares high, that equals now an inspiratory reserve volume of 3 liters. 3 liters. Okay? The vital capacity is going to equal the tidal volume plus the inspiratory reserve plus the expiratory reserve. So if you add those 3 volumes together, or if you want to count the number of squares, what you'd come up with is 4 3/4 liters. And you can count the squares and verify that that's correct. So it goes from here all the way to there. The residual volume is going to be the amount below this lower valley. So if you count the number of squares here, what you come up with is 1 1/4 liters. 1 1/4 liters. The total lung capacity would be the amount of volume from the very bottom of the horizontal axis all the way up to the very top of the vertical axis, and that is 6 liters. 6 liters. Okay? So with that in mind, we can compute a couple of things. Actually, if we go back here real quick, another thing we can compute is also the number of breaths per minute. Okay, so how do we measure that? Well, we measure that taking the tidal volume. Excuse me. And the tidal volume, the tidal respiration rather, is going to be this area here. Okay, this area here is blocked off as representing a total time lapse of 15 seconds. So in 15 seconds, this individual took 1, 2, 3, 4, 5 breaths. Well, if they took 5 breaths in 15 seconds, the number of breaths that they would take in a minute would be 20. And that would be their respiratory rate in breaths per minute. So we can go ahead and add all these figures in. You can see that I've entered the data here. Okay, and we can also calculate something called the minute air volume, which is expressed as the respiratory rate times the tidal volume, which would be 20 breaths per minute times 500 milliliters per breath, and that works out to 10,000 milliliters per minute, or 10 liters per minute. Okay, that brings us to the end of this podcast. Be sure and review this material, and be sure and take advantage of the resources that are available at Biosis and during lab to prepare you for the practical. I'll see y'all Saturday.